Let's take a look at a Python SymPy example. We would like to see how the product P of A of Z is equal to FA times D of C times G of Z of our folding matrix FA of Z with the zero delay matrix G of Z look like. So here I'm importing SymPy. I'm defining symbols for Z, symbols for G, and symbols for H. Here's our FA matrix. Here's the D matrix. Here's the G matrix. So we're just printing them here. And here we have the multiplication of FA times D times G. It's given here. And we can see that this is indeed the diamond-shaped form of equation 1. But when we compare it with equation 1, we could now read out the resulting final baseband prototype filter for the analysis H of A. Observe that equation 1 is for an even number of zero delay matrices. For odd numbers, as in this example, we would need to flip the matrix in equation 1 horizontally. So we'll flip left, right. So now we don't specify H of A in our design process, but we start with our coefficients for our matrices and obtain a baseband prototype filter H of A with the desired length and delay properties. What is a possible drawback of these zero delay matrices? If we only increase the filter length with our zero delay matrices, we can observe that the far-off attenuation increases easily, a clear improvement over the mdct case. But the nearby attenuation to the neighboring subbands increase not as much as for orthogonal filter banks with similar length but with more delay. Hence, it can make sense to also increase the system delay to obtain filters with higher nearby attenuation more easily. This leads us to a matrix which is very efficient in increasing the system delay, the opposite of zero delay matrices. The so-called maximum delay matrices. They basically result from exchanging z to the power of minus 1 by z in our zero delay matrices and a multiplication with z to the power of minus 1 to make them causal. So this is what we are doing here. This is one type of matrix. Each matrix in our cascade has its own coefficients. The other type is given here. Their inverse need a multiplication with z to the power of minus 2 to make it causal, and is correspondingly this one here and this one here with the multiplication of z to the power of minus 2. Here we can see that the matrix and its inverse leads to n blocks of delay. So we have here and here. Observe that the maximum delay matrices have a polynomial order of 1, just like the zero delay matrices, and hence increases the filter length by 1 block, but increases the delay by 2 blocks. This is twice as much as for an orthogonal filter bank. Using only maximum delay matrices would result in similar frequency responses as with only zero delay matrices. The impulse response would only appear time reversed. We get increased nearby attenuation only if we mix both types of matrices. Orthogonal filter banks can be obtained if we use the same number of maximum delay and zero delay matrices. Our resulting polyphase matrix for the analysis then becomes this product, given here, where H of M is either the H1 of Z if B is even, or H2 of Z if B is odd. For the synthesis polyphase matrix, we get the inverse product, and the result is given here. Now we can design the impulse response length and the system delay of our filter bank. The total number of our zero delay and maximum delay matrices determines the length of our impulse response, including the effect of the FA times D of Z matrix, a length of n blocks, and we obtain a total filter length equals to L equals to 2 plus Q plus P times n. And just the number of maximum delay matrices HM of C determines the system delay, including the effects of the matrix multiplication FA times D to the power of C and the blocking delay with a delay of 2 times capital N minus 1, and we obtain a system delay equals to ND with 2 times N minus 1 plus 2 times Q times N. Each zero delay and maximum delay matrix increases the impulse response length by one block of N samples, and each maximum delay matrix increases the system delay by N blocks, so 2 times N samples. In this case, starting with the mdct delay of 2 times capital N minus 1 samples. It is also possible to start with a lower delay than an mdct by setting the leading samples of the mdct type part to 0. Observe that we obtain the same analysis and synthesis baseband impulse response if the determinants of our submatrix of our polyphase matrix are equal to minus 1 as seen before. If we look at the zero delay matrices, we find that the determinant of the submatrices is already equal to minus 1, and it's very practical. If we look at the maximum delay matrices, we see that their determinant of the submatrices is minus z to the power of minus 2, which is their resulting delay contribution, and a factor of minus 1, which has the same effect of leading to the same analysis and synthesis impulse responses. All we need to do now is to make sure that the matrix FA has a determinant of minus 1 in their submatrices to obtain identical analysis and synthesis baseband impulse responses. This means that the number of unknown coefficients for the folding matrix FA is going down from 2 times capital N to 2 times capital N minus capital N divided by 2. So the remaining capital N divided by 2 coefficients come out of the determinant equals to minus 1 condition. This also makes the design easier because then we only need to optimize one side of our filter bank. For instance, the analysis side, and we have a reduced number of coefficients. We need a numerical optimization because we now have a long cascade of product with many unknown coefficients in the FA folding matrix, the zero delay and the maximum delay matrices. We need to optimize them such that we obtain a good frequency response for the resulting impulse response. We can use equation 1 in this lecture and our product for the folding matrix FALC without the transform matrix T to read out the resulting baseband impulse response HA of N. We can then compute the resulting frequency response and use that as a function to optimize towards some optimum frequency response, for instance an ideal low-pass filter as the prototype. An example application of this type of filter bank is the audio coder enhanced low delay AAC in MPEG 4, and here it is used to obtain a lower encoding and decoding delay.